What happens when high school students and MIT graduate students team up to study the Northern Lights? Magic! Today, we're meeting with Jared Rivera, a graduate student in plasma physics who will tell us all about his research, the Northern Lights, and about some very special cameras.
Hey everybody, thanks for coming to this abstract, whether you're here now or tuning in on YouTube later. My name is Jared. I'm a fifth-year PhD student in the physics department here at MIT, and I want to tell you a little bit about the colors of the Northern Lights. So I'll take you through a little bit about myself, about a project that I've been a part of for the past couple of years, dubbed the Geophysical Plasma Observational Expedition, or the GPOE. We'll get into what that means. And then I want to talk a little bit about how you go from observation of natural phenomena to control in the lab and for applications to technology. So a little bit about myself. I was born and raised in Southern California. Always really enjoyed getting outside and spending time in the outdoors. A picture of Joshua Tree, one of my favorite national parks, is out on the right. And when I was early in high school, a friend gave me the book A Brief History of Time, which is a kind of a primer on modern physics. And it was a really impactful book for me and kind of charted the course, whether I knew it or not, for a lot of what I would be interested in and working on later in life. After high school, I wanted to attend college, but I wasn't sure exactly what I wanted to study yet. I came into college undeclared, meaning I hadn't chosen a major. So I was at the school, but didn't have a degree program I was a part of, and ended up spending a lot of time doing a lot of different stuff over the years. So in the beginning, I was interested in environmental science and the researching climate change and whatnot. So me and one of my roommates and coworkers down on the bottom left, working in a bog, trying to study biodiversity. Spent some time learning about material science and the way things break. So up on the top right is a picture of basically a simulation of a bullet smashing through a target, studying how these fractures and how cracks propagate. And eventually, I ended up getting interested in engineering and declaring a major in civil engineering. And for a short time, I worked on building foundations for buildings in Los Angeles. So there's a picture of the types of sites that I was working on the bottom there. But after a while, that interest that I mentioned in physics kind of came back, and I decided that I really wanted to pursue a direction there. And in the process, I particularly got really interested in working on electronics and working with lasers. And there's a really interesting field of physics called atomic physics, where you build electronics and you use lasers to study the properties of atoms. And so on the right here is a picture of a cloud of atoms trapped and levitating, and they're glowing because they're being illuminated with laser light. First time I saw a picture like that, I was sold and said that's what I wanted to do. So I applied to MIT for a PhD and came and started working on atomic physics. And the goal of my lab is to study really low temperature phenomenon, right? So the atoms and the molecules in the room that you're in right now are moving around at about 300 meters per second. They're really fast because they're pretty warm. And how hot something is tells you how fast things are moving around. If you want to trap and isolate atoms, you need to get them very cold. And so the bottom left here, the CUA, is where I work, the Center for Ultracold Atoms. So we use lasers to cool atoms down to almost absolute zero, minus 273 Celsius. And there we're able to study the atoms in isolation for the most part. So on the right are some pictures from the lab that I spent the first few years of my PhD putting together, laser systems, the apparatus where they're trapped, microscopes to study the atoms, and so on. So in these ultra-cold atom laboratories, when you're dealing with the ultra-cold atoms, there's a solid chance that the sample you're working with is the coldest thing in the universe at that time, which is a pretty cool thing to be a part of. But there's also lots of different physics going on in the field and at MIT, and particularly right now all around us. So some of you, especially if you're living at the higher latitudes, may have seen the aurora in the past couple of years. It's been a really good couple of years to see it, and there's some really interesting reasons for that. Aurora is a geophysical plasma phenomenon that basically just means it's a plasma created on Earth, and a plasma is a gas where something really energetic has happened to it. It's either really hot or it's collided with something, one of those things. The sun is a big glowing ball of plasma. And particularly, every 10 years or so, as you can see from this plot in the bottom right, the sun gets a lot of sunspots on it. and when it has lots of sunspots, it spews this plasma towards the Earth. And right now, in 2024, 2025, we're at the peak of sunspot activity. And that means a lot of more plasma is coming towards the Earth, and we're getting a lot more aurora. Specifically, the sunspots kind of spew off the plasma in these really big arcs. You can see on the left here, the Earth is just tiny compared to the scale of these phenomena. And when the solar wind, the plasma that's blasted off the sun, smashes into the Earth, the particles come down into the atmosphere, make a plasma in the upper atmosphere, 100 kilometers in the sky. And when they knock the electrons off of that gas in the upper atmosphere, that's when the aurora happens. There's light emitted by those atoms and molecules, and you see that at these very specific altitudes, specifically near Alaska, northern Canada, and then it also happens near the South Pole, so the very southern tip of Chile and maybe the northernmost parts of Antarctica. So, me and some of my friends who were in physics thought, wow, this sounds like an awesome opportunity to learn about some type of physics that we don't typically interact with. And so we said, this calls for an expedition. Specifically, some of you may have seen an abstract by Sean Mackey. He's a plasma physicist here at MIT. He's one of the principal organizers of this trip. And so we kind of rallied a crew together and said, let's go to Alaska, let's see the Northern Lights, and let's take some measurements of it. We decided to do this pretty late last year. So we had a couple of months to figure out our plan, build all of our detectors to do the measurements that we wanted to do. And so we had a very rapid process of prototyping for that. So on the bottom left here, you can see our first concept drawing for what's called an all-sky camera. It's a camera with a fisheye lens that lets you see the whole sky at once. Soon, John, one of the expeditioners, put together a better design for it. And then not too long after that, we had a completed system that we were going to use. So on the bottom left, you can see it when it's deployed, nice tripod and insulation and everything. We also had other detectors that we wanted to use, right? So not only can you take pictures of the aurora, but you can study the kind of colors that come off of it. So we wanted to use a spectrometer, which breaks down the color of light that enters it. So we hooked that up to some binoculars that we could point at the aurora, capture the breakdown of the colors. And we also wanted to take radio measurements of it because it also emits radio waves. So here's each of those instruments being deployed when we were out in the field. So we've got Tucker on the left servicing the all-sky camera, me and Sean after we pointed the spectrobinos, and then Skylar, our resident radio expert, deploying our first radio out in the field. And it was a wonderful success. We captured some really cool pictures, got some really cool data, and saw some really beautiful aurora. So these are all taken at Poker Flat. It's a research range operated by the University of Alaska Fairbanks. And we were really lucky to have really clear nights, a new moon, so there was no moon in the sky, and really, really active geomagnetic storms. And one thing that's really interesting is the aurora being a plasma, kind of like an electromagnet, when it comes overhead, it makes huge changes in the magnetic field on the ground. So if you were holding a compass and the aurora showed up overhead, the needle would start jiggling and pointing in different directions. And so that's one of the things we wanted to measure and saw. The spectrobinos, like I mentioned, we're going to break down the color of the light. So visible light is everywhere from about 400 to 800 nanometers in wavelength. And green, that color green, occurs in the high 500s, red is in the high 600s, and blue and purple are down near 400. And you can see these little spikes where you would expect purple, green, and red to be. But you can break this down even further and pull a lot of really cool information about, the atmosphere itself out of these colors. For example, you can specifically find these lines. So these little spikes in the data, the blue solid line, correspond to where these dotted lines are. That's what you would expect if there was hydrogen. Similarly, you can see a really tall green peak, super tall one from this one, right where you would expect oxygen molecules to show up. And there's also features that are highly reminiscent of nitrogen. So you can spend a lot of time breaking down all the different colors that are present and what you can expect about the atmosphere. But basically you can find, that there's all types of molecules and ions of different species up there. You can extract the densities, the temperatures, tons of information just hidden in the color of the aurora. So not only is it beautiful to see, it carries a lot of information with it, which is really cool. We're planning to go back. We have a expanded research goal this time, partially due to collaboration with the Nord Anglia. So we're very grateful for that. We're going to be not only in Fairbanks, but we're going to spread out across all of Central Alaska to try to do distributed measurements. We're not only going to bring one all-sky camera, but 17. And these were built with the support of a bunch of high school students. So those are on the bottom right here. And in testing them, we had to focus these cameras. So shout out to the British International School of Boston and their teachers specifically. But we're very excited to field these next January. So the aurora is beautiful and we can take all these measurements, but there's also a sense in which, what's the point? How does this relate to what I do? Are there any implications for technology or how to apply this information? And the answer to that is yes, but it comes in a surprising way. So just by observing the aurora, you don't necessarily know that there's going to be a technological application, but when you kind of dig into the why question, why is it the color that it is? It takes you down this long road. So if you were to take light, put it on a prism and break it up into its colors, kind of the way droplets of water do in a rainbow, you would expect a continuous line from purple to red. But when you actually measure light from the sun, for example, that's not what you see. There's these little lines missing in the spectrum. You can see that on the bottom left. And when you dig into that question, why are these lines missing? The entire field of what we call quantum mechanics falls out. And it's a beautiful 100-year history, but basically what it led to in part is people saying, I need to recreate the conditions of the sun or the interstellar medium in the lab and study what's going on. And in the process, a lot of really interesting technologies developed. This technology includes things like transistors, which are in the CPUs that make your computer run. It's related to MRIs, which is used by hospitals, nowadays full-on quantum computers, and then specifically by understanding why the colors come out of certain atoms, you can control them, and that's what I do. So on the bottom right is, an example like I showed earlier of those trapped atoms, and this is me kind of trapping and controlling them in the lab. So just by observing and asking those why questions, you can get a lot of technical control over these physical phenomena, and that's fascinating and has tons of technological applications. So in summary, one thing I hope you take from this is that science is multidisciplinary and the science itself and your path into it can be nonlinear. I would say if you're living in the high altitudes, it's a great time to see the aurora, so try to get out specifically at night. And there's really interesting science that exists across all scales. It's all related from things happening in the cosmos to the technology in your phones. So with that, I want to briefly hint at some of our goals for the 2025 expedition, specifically related to what we call tomography. And maybe we can get into detecting muons, which is one of our goals for this coming year.
Thank you very much, Jared. Wonderful photos. Thank you so much for sharing that really cool research with us. We have a bunch of questions in the chat, but I wanted to kick off with one regarding something you just mentioned. What is a muon and why are you interested in it?
Yeah, so a muon is a really interesting fundamental particle. So atoms are made of subatomic particles, specifically electrons, protons, and neutrons, but there's tons of particles, and one of them is the muon. It's like an electron, but heavier. So it's like the heavy cousin of the electron. And because it's heavy, it's unstable, and it decays into electrons. But one thing is that they come from all types of cosmic phenomena, and they come into Earth all the time, like you're being bombarded with them right now. But specifically, one thing that's really interesting is when there's high solar wind activity, the Earth is more exposed to muons. And so one thing we want to see is if when we see the aurora overhead, do more muons show up? So one of the new members of our team, Alex, is building some muon detectors for us to try to dig into that.
Got it. Thank you so much. And on the aurora and on looking at it, you showed really wonderful pictures. And we have a couple of students, Aishwarya and Aya, and they're both wondering, do the northern lights, do they change in color? Do they have certain patterns? I know we looked at photos, but you got to see it in real life. Could you tell us about it?
Yeah, absolutely. Great questions. The colors actually depend on a lot of things. So they depend on the composition of the atmosphere, the altitude at which the gases are emitting the light, and what's causing it. So the solar wind is what I said causes it, but the solar wind is just anything that's being boiled off the sun. So this can be protons, it can be electrons. The electrons come in really fast, penetrate really far down into the atmosphere, and that's typically where you get the green color from. Protons, for example, don't make it as far down, and they cause a more red color to occur higher in the atmosphere. So that can be changing in time, and you definitely do see sometimes purples show up and go away, or sometimes it's more red or green. So yeah, it evolves in time a lot, and it's a changing phenomenon as the night goes on.
That is really cool. And now we have a question from Juan, who's, also very curious about these colors. And Juan's wondering, what is the most rare element you've detected when you're trying to figure out what's making those colors?
Um, what's funny is it's not a rare one at all, but it's the most surprising one, if I can answer that way. We expected to see nitrogen, oxygen, basically those. But those first lines I showed, those really narrow vertical ones corresponding to hydrogen, those weren't coming from the aurora. Most likely they were coming from just deep out in space or maybe sunlight reflected off of the moon. And frankly, at first I thought it was just noise in the data. But it lined up so well with where you would expect the light from hydrogen to be that we were like, well, that kind of must be it. And that was very surprising that we were able to see it, particularly because it wasn't a sophisticated device. We just put the spectrometer on a pair of binoculars. And so being able to see that was a really exciting moment.
That is really cool. And now we have a question from Daria, and Daria's wondering, why can't we see the auroras anywhere? Why are we only seeing these at the higher latitudes, like you mentioned?
Yeah, good question, Daria. So the reason for that is the Earth is kind of like a bar magnet. So if you imagine the magnetic field lines coming off a bar magnet, they go like this. And if you imagine putting that bar magnet inside of a sphere, which is like the Earth, the charged particles of the solar wind like to follow magnetic field lines. And so where those magnetic field lines strike the sphere, that just so happens to be in what we call the auroral oval, which is at a pretty specific latitude. So it's all based on the geometry of the magnetic field lines coming off of the Earth and how those interact with the magnetic field lines from the sunspots.
Got it. And so what if I live in the southern hemisphere? Can I ever see anything like this?
Yeah, the auroral oval exists at, both the, I guess, north and south side. And the auroral activity is correlated at both. So if you're seeing a lot of aurora up north, you're probably also seeing it down south. And you can find some really cool images that have been taken with like satellites and planes showing that it's happening in both places at the same time. Unfortunately, the southern auroral oval, and down there it's called the Aurora australis, doesn't really occur where a lot of people live, and a lot of it is over water. So it's much harder to observe.
Okay, got it. So hopefully we can all see it up north someday. Now we have a question from Paulina, and Paulina's wondering, can you predict the colors that the northern lights will be before you could see them based off of other things you're measuring, perhaps?
Yeah, that's a good question. One thing is that if you're looking at the sun and monitoring the sunspot activity, that's a good predictor of when there's going to be auroral events. Um, our group has never tried really doing that in detail, so I can't say for certain, but I th I would assume that if you're seeing lots of sunspot activity, you would expect a more energetic event, and that would be more green. But that would be a good thing to test.
Maybe that's the next research idea.
Mhm.
We now have a question from uh, Ms. Jesperson's class, and they're wondering, you mentioned the dependencies of the colors on the atoms and the components in the sky at the time, but do the different shapes of the auroras mean anything? And if so, what causes the different shapes and distributions you see of the light?
Yeah, no, that's a great question. So like I mentioned of why the aurora occurs where it does, the solar wind, or what we call these primary particles, are following magnetic field lines. So typically, there's a nice kind of well-structured magnetic field coming down towards the ground at these high latitudes. And you get some beam of high energy electrons or protons coming from the solar wind. And that's what makes the long curtain shape of the aurora. So that's kind of showing you where that beam is striking. And then when it cascades downward, make that kind of curtain towards the ground, that's those particles being bent downward. So like a single primary is coming in and then shooting off towards the ground and then abruptly cutting off about 100 kilometers in the sky. So what you're kind of seeing is the path that all of these particles from the solar wind have taken, and it's tracing out more or less what the magnetic field landscape is in the sky. So it's telling you about, the densities of different things, about the shape of the magnetic field, and about kind of where particles are coming in from the solar wind. So there's a lot going on there and a lot that's still kind of unknown, which is why it's a really exciting field of research.
That is really, really cool. And so we've talked about the heights in the atmosphere in which this is happening, but in terms of the like horizontal spread, how big are these auroras? How many people can see them?
Yeah. What's crazy about these is that they have a lot of different, what we would call like characteristic length scales, or maybe none because they spread out across so many scales. So, a curtain can extend basically all the way across North America, or, large portions of it, hundreds of kilometers. And then it's going to be, maybe 100 or 200 kilometers tall, but then also maybe just a few wide. So it's already kind of got a crazy aspect ratio, but then it's got lots of substructure to it. So, people take measurements from satellites and try to take pictures of the whole Earth at once to see what's going on. Some people do, much more professionally, to be honest, what we're doing, taking pictures from the ground and trying to see what we would be able to see from a ground-based observation. And then some people care about the really fine structure of it. And so there's a really cool research program where they launch rockets into the aurora to try to touch it and measure it and see how things change over shorter length scales. So it's very big, but it's also very finely detailed. There's a lot of structure to it.
That is really amazing. And that leads me to a very philosophical question from Tiara. So Tiara's wondering, when you, Jared, watch the Northern Lights, do you ever think about the other people who you love maybe watching them? Do the lights make you feel connected to everyone who's, standing in their amazement?
Yeah, no, that's a great question. Specifically last year, I had an uncle that was living in Alaska, and so I was texting him a lot, and I was excited that I got to see that because that was something that, he had seen a lot and I had never seen before. And then, yeah, that question about connection with other people who are seeing it, our whole group, we had spent a fair bit of time reading over the different like folklore and ideas over what is the aurora and why is it caused over, people from all throughout time and all across the world, and seeing different people's interpretations and different cultures' interpretations of it was a really fascinating thing. And that's a very connecting thing as well. You've got people in Babylon and China 500 or in 500 BC all the way through, Inuit in the past 2,000 years. There's tons of people who have stared at this and pondered it and thought about it. There's cave paintings about it in France and stuff. So, people have marveled at it for a long time, and it's cool to be a part of that kind of continuous process.
Absolutely. It's incredibly special. And now we have a couple of questions from Jason and Paulina, and they're wondering, can the Northern Lights or can these phenomenon be found on other planets? Is it just an Earth thing?
They can absolutely be found on other planets. Yeah. I think as long as you have the right magnetic field conditions and an atmosphere that can be ionized, I would expect that you can. And I think specifically it's on, I want to say it's either Saturn or Jupiter. There are great pictures of it, so you should look it up. People have gotten pictures with telescopes. I'm not sure if they're satellite based or what, but yes, it does occur, and there are great pictures of it, which are super cool to see.
I'm going to look those up right afterwards, along with all the other Nord Anglia students on this call. We now have a physics-related question from Paz, and Paz is wondering, could you tell us a little bit about the heat that's generated during this process? Is there heat generated by the Northern Lights? The reason they're asking is the sun is a big ball of plasma that provides heat and light to its surroundings like us. So do the Northern Lights do the same thing, or is this a different process?
Yeah, I mean there is energy being deposited on Earth in this process. So you've got these particles that are streaming in, they're bringing energy to the Earth that wouldn't otherwise be there, and it's being dissipated in the atmosphere as these primaries slow down and as they emit light towards us and back out into space. I don't have a great sense of the number off the top of my head. It's not like some crazy important amount of energy, but it's enough that people that work on satellites, for instance, care. These solar wind disturbances can mess with satellites, which would have impacts on our GPS and whatnot. So, it's enough that we care about it, how the way it could impact our technology, but, it's not to the same extent that, we utilize the sun's light for solar light or for solar energy and so on.
Got it. And so you mentioned that it does have this effect on satellites, and there are some folks who, worry about interference there. That leads us to a question from Paris, from Boston, and Paris is wondering, how do people know when the sun is going to be active like this? Can you tell in advance when this is going to happen, and how accurate is that?
Yeah, that's a good question. I frankly do not know tons about the kind of dynamics of the sun with this, but there are a couple of fairly regular cycles. So there's an 11-year or 10-year cycle that the sun goes through, where these sunspots are very active. Really cool tidbit about that. That's related to the geomagnetic poles of the sun flipping. So the north and the south pole flipping up and down. And there's also these longer 100 or 200-year oscillations as well. Beyond that, I know people do space monitoring of the solar wind and whatnot to try to do predictions of the impacts that you would have here on Earth. But yeah, it's one of those things that, it's a complex phenomenon, and I'm not too sure of our handle on it.
That is completely fair. There's a lot to learn and a lot to study there. Now we have a question from Jose at the Colegio Menor, and Jose's wondering, do auroras also reflect or emit non-visible wavelengths too? Have you been able to measure things that we can't see with our eyes?
Yeah, great question, Jose. Yes, the spectrometer that we used did extend into the ultraviolet, so shorter wavelengths than the blues and the purples that we can see, and the infrared. And yeah, there was light at both of those. And there are, I think specifically from nitrogen molecules, there's some UV light that you would expect. And I don't remember the species, but there is some infrared light that you would expect as well. So yes.
All right, so there's a lot more going on than we can see. That's really special. And now we have a question about connections to quantum physics from Adam. And Adam's wondering, what are some key areas of overlap between the quantum physics you study and the Aurora Borealis? Adam seriously wants to study quantum physics and understand this. So they also wonder if you have any advice on that overlap.
Yeah, totally. In my mind, the overlap is related to what you would call spectroscopy. So the effort of looking at a material, or if that's just atoms or molecules or gas, whatever it may be, and trying to understand its structure by probing it, in this case, with light. So in this case, there's some phenomenon and light is being emitted and we're measuring it. In the lab, I kind of do the opposite. So given, the structure of some atom, or if I want to understand the structure of an atom, we use lasers and tune them to the right frequency, the right color of light to be able to manipulate the atom or control it or study it in the way that's appropriate for that situation. But in both cases, understanding the light that comes out of the atoms and the molecules in the aurora, or for controlling them in the lab, it all comes down to the structure of the atom or the molecule. And that is entirely governed by quantum mechanics. And it's the same quantum mechanics in both cases. So understanding why an atom or a molecule has the structure that it does kind of enables you to do either side of that, do observations or control them in the lab. So it's the same physics.
Got it. And now, given that you're in the lab and you're looking at these atoms and it's ultra cold and everything is slowed down, you showed us some of the pictures of the colors that you can see. Do you have a favorite atom from all of this? And can you tell us about the color it makes?
Yeah. So the two atoms that I work with right now, I would consider tied for my favorite. Um, the first one is lithium, and the dominant color of laser light that we use to control it is red light. It's 671 nanometers. Um, and lithium, there's lithium-6 and lithium-7. That's the mass of the nucleus. So one of them has a different number of neutrons. So that's my first favorite. It's a very light atom. And then my other favorite is erbium. It's a very heavy atom, way down on that weird two rows on the periodic table that are separated from the rest of it. It's called a lanthanide atom. Um, the colors that we use to control it there are gold at 583 nanometers and blue at 401 nanometers. And a really fun fact about erbium is most of the erbium and the other lanthanides that you see in the universe were made in the collisions of neutron stars. So it takes these really exotic astrophysical phenomena to even make that element. And we have it, and it might be, helping us talk over Zoom right now. It's in optical fibers and stuff like that. So it's, it's used all over the place, and it comes from these really exotic, crazy environments.
Those are very good picks. I think we're all going to be researching those metals afterwards. And now we have a couple of questions about working in the North and in Alaska. So first, from Miss Jesperson's class, how was the experience of living and working in the North? Of course, it's fascinating and beautiful, but was it difficult when you were there?
Yeah, so we were only there for a short time, and we'll be going back also for a short time. It's just a number of weeks. But yeah, it's cold and it's dark, and there are people that do this type of work, all year and for, a big portion of their career. So I have to give big props to them because, it's a blast and it's interesting, but hanging out at, minus 40 degrees and, having only a few hours of daylight a day, I don't know if that would be the full-time thing for me, but, some people do it and that's really cool. But yeah, it's, conditions that are a bit irregular for most of us.
Of course. And then another question from Miss Jesperson's class is, does the cold help the northern lights appear because it's slowing down atoms? You kind of described that phenomenon. Is that helpful in this case?
That's a good question. I'm not sure. I don't think so because this occurs so high in the atmosphere that I don't have a great sense of how different the kind of the weather there, the temperature is across latitudes, but it's 100 kilometers up. So it's, way higher than you're going to be with airplanes or anything like that. So pretty cold everywhere up there, I would say.
That sounds, yeah, pretty freezing. We now have a question related to the cameras that the Nord Anglia students helped build as part of this research project. So Megan from Boston is wondering if you'll take Olaf with you still. And this is,
Olaf.
yeah, it's the name of the camera she made during the pilot study.
Yeah. Hi, Megan. Yeah, we have all of the units that were made at both build days. I think a couple from the first one are in a little less of a state of repair since we still have to work on them, but every camera that was made, we're planning to bring up, and we're putting together a website with a tracker that's going to show where all the cameras are deployed with the team names on them from the most recent build day. Those are all different animal names. So, shout out Team Worm, Team Axolotl, all you guys. Look out for your cameras on the website.
That's wonderful. And just to give us more context on that, how many cameras were made during that MIT student trip that you'll take with you?
Yeah, it was 17. So last year we just had the one and we were taking these nice, beautiful pictures. This year we're going to try to deploy all of these ones that were built. And the goal there is to take simultaneous pictures from all across central Alaska to try to rebuild the 3D shape of the aurora. Kind of the same way that a CAT scan takes pictures of you from multiple angles and then rebuilds kind of the 3D picture of what's going on in your body. We're going to try to do that with the aurora by sending cameras out on a big, 100 by 100 mile grid.
That is totally awesome. I cannot wait to hear about how that goes. Now I wanted to shift gears a little bit into your journey to studying quantum physics and the aurora. So I'm going to take you all the way back to high school because Lilia from
Mhm.
Boston is wondering, what extracurriculars did you do in high school, and did any of them link to what you're working on now?
Um, I did extracurriculars. I would say none of them really relate, to be honest. I played sports. For a period of time, I was on like the speech and debate team, but I was never involved in like science Olympiads or anything like that, and I wasn't even exactly sure what I wanted to get into, but I've always been motivated to try things that I'm interested in, and that kind of is the reason I had such a meandering kind of pathway into this. So, um, yeah, it was sports and various clubs, but no really science extracurriculars aside from I took AP physics when I was in high school. But that was the only real exposure I had to physics until college.
Got it. So we kind of come to our research and our topics, not necessarily in linear ways where everything is started early on. We develop these interests over time.
Mhm.
And so can you tell us about the moment you decided to study physics? What happened in college? Did you have a particular professor or experience that helped you reach that?
Yeah, I had lots of good professors both in the engineering program and in physics, but I would say it wasn't so much particularly a specific professor. There was maybe two moments that made me want to do physics for the most part. When I was finishing my engineering degree, I'd put off one of the physics classes because it wasn't very relevant to what I was doing. And so I was like, okay, I have to go finish this up. And when I got to the end of it, I was a little sad. I was like, oh, that's maybe the last physics class I'll ever take. And I've really enjoyed doing those. And that moment really stuck in my head. And then the other one was I had a roommate who was doing the same type of physics that I do now. And he told me about what laser cooling is, how you can use lasers to cool atoms from room temperature or even hotter to absolute zero. And that sounded like such absolute science fiction to me that I had to know more. So those two things were happening around the same time. And I was like, well, maybe while I'm in college, I'll take some more physics classes and I'll just kind of see where this goes and, try to keep learning physics as long as, is reasonable. And I'm still doing it.
That is totally wonderful. And now I do have a question from Panika, and Panika is wondering, based off of all of this knowledge you're gaining throughout your experiments, uh, can auroras be artificially created? Given that you know information about density, temperature, atoms, the conditions, can we make auroras?
Yes. Yes, decidedly yes. It can be done a number of ways, but yeah, if you look up, artificial auroras or artificial air glows, they can be made those ways. A kind of creepier example of it is that they can be caused by, you know, large scale energetic events. So there was an example of a super high altitude nuclear bomb detonation that did result in auroras. So yes, they can be, and some of them are done for research as well.
Got it. Could now, just to close us off, we have so many more amazing questions in the chat from who I think are very a great number of future quantum physicists. And I wonder if you have any insight or advice that you'd like to share with them as they develop their careers in physics.
Yeah, I would say do the problems. It's very enticing to, just keep falling down the rabbit hole of all these different physics phenomena by, you know, reading about them and watching YouTube videos and all that stuff. But I would say the most rewarding part of physics for me is when I can actually feel like I understand it and actually be able to calculate something. So whether that's your homework problems or, when you're reading a textbook or anything like that and you don't understand what it is, do the math. It's going to help you down the road. And math is the language of physics. So if you want to do it, you gotta, get your chops up there.
All right, and there it is, folks. We're going to do all the math problems after this, and we're going to look at auroras on other planets. That's our homework for today. And now I want to remind folks that we have one more abstract this season. We're going to be joined next time by Sydney Johnson, who's going to tell us all about clean steel for real. And with that, I wanted to thank the Nord Anglia community for asking such wonderful questions today. I'd like to thank the MIT Nord Anglia Education Collaboration for making this wonderful series possible. And of course, I'd like to thank Jared for sharing his excitement and passion in research with us today. Thank you very much, Jared.
Yeah, thank you all.
All right, see you all next time. Goodbye.